Alrighty, welcome to IM1 for LP 9, days 1 through 5. We're going to be working in chapter 13 this week. So as always, I'm going to start off with class expectations. So make sure you understand, how the grade is weighted. Homework is definitely the most important as far as point value goes because it's worth 50% of your grade. So we do need to make sure we're logging on to alex.com and working on our homework assignments. And you'll notice when you go into either assignments or gradebook, you will see the word homework next to the assignment. Topics, this is what we do every week. You get 10 topics, and that's based on you, how you performed on the initial knowledge check when you first took that. And so these topics are meant to help bring up your math level, your math knowledge there to help you with your homework and tests and quizzes. So tests or quizzes, that's either one or the other on Monday. Just depends on if we're still in a chapter, we would have a quiz. If we've ended a chapter, then the next week we'll have the test. But they're definitely, each one of these, they're worth smaller chunks in the homework, but, they're definitely worth enough that it makes a big difference if we're not working on them. Because if we haven't done any of the tests so far this semester, that's 20% of your grade that's kind of being held hostage. You can't have it until you do those tests. So it's counting against you, but it's definitely not helping you to not do those items. So if you have any questions about that, please reach out and ask. Attendance, yes, make sure you're coming to class. I know we've had a little bit of a spotty semester here with some of the different schedules we've had to accommodate, especially with some of the state test schedules over the last couple weeks. But we will be going back to class here in the next week and then be able to end out the semester. And then work completion, of course, make sure you complete all your work on alex.com because we're not doing any of the classwork for this week, specifically because we're not in class this week. But all work is due on Sunday. If you need extensions, just let me know. You do get an automatic week extension, but let me know if you need any extra extensions because I can't extend any of the assignments except for topics. That's something that Alex calculates on a weekly basis. So even if I extend it, it won't actually go back and count it for you. So that's the only one that doesn't get extended. But the rest of them, homework, test, quizzes, they could be extended. No late penalty or anything like that. You just go and work on it and you get your points for it. All right. Resources, huge one. Make sure you're using your resources. Your teacher, me, and your independent study teacher are your first resource there. You can reach out and ask us any question you would like. And we will do our best to help you there. Your notes pages. So if you have not received your notes pages for this week, please reach out to either me or your independent study teacher to get your notes pages. Because that's what this lesson is going to be based off of. In-center tutoring, we do have an in-center tutor, and you can always come and ask me for help too as well, because I usually have some time before or after class. We have the FEV tutoring, super easy to use. That's this, nice bright piece down here. You go to clever.com and you find this little logo. It's a little smaller there, and when you click on it, it logs you in, and at the very top, you can say on-demand session. It asks you what you're asking for help with. Very easy question to answer. I need help with math and in this subject or this concept. And then it starts you up and you can immediately start working with a tutor. And then when you're done, you just let them know you're done and you log out. It is a very, very easy program to use. I also made YouTube videos for all of your homework. So yes, I did all that homework too. So make sure you're using those. Those are the QR codes that you'll see at the top of your notes page, but you can also get to them from the Google Classroom. They're all listed in there as well. If you bookmark my YouTube page, then that is an easy way to find that as well. And then, did you know you can ask questions directly from alex.com to your teacher? So when you're in a test, a quiz, a topic, or homework, there's a little envelope on the right side of your screen, and you can click on the envelope that's on the right side of your screen. It will open an email directly to me, and you can type a message. It attaches a picture of what you're working on, so I know where to go help you. It's a very convenient way to ask questions. All right, let's go ahead and get started here. So this week we're getting into chapter 13, and this is all about parallelograms, or, we're going to do quadrilaterals first and then kind of get into parallelograms. So our first practice problem here is about the sum of the angle measures of a quadrilateral. So quadrilateral, if we kind of take a step back, quad means four, lateral means side, so we're talking about a four-sided figure. So that's kind of just breaking that piece down. Sum means that we're going to add. So we're going to add the angle measures of a quadrilateral. And this is the interior, the inside, right? So the sum of the angle measures of quadrilateral is 360 degrees. If you remember before when we were using a triangle was 180. Well, if I connect any two of the diagonals here, or the vertices, I make two triangles. So 180 plus 180 is 360. So it's kind of an easy way to remember that. Why is it 360? Because it's basically two triangles. All right, so, and this is going through, so a quadrilateral has four sides. So we have our four-sided, and I'm just doing a rectangle here. We can divide that into two triangles by connecting. So this is the visual that I just talked about. So I can connect either diagonal, and I get two triangles. So 180 plus 180 is 360. Sorry, I should have been clicking on that as I was talking. So this one, that kind of popped up a little quickly. So we're just going to add all of these up. Well, I'm missing one, right? I need to find the value of x. So if I know that x plus 105 plus 80 plus 39 has to equal 360, no matter what, if I have a quadrilateral, a four-sided figure, the four angles have to add up to 360. And this is what we call this a convex polygon instead of a concave. So concave would be like if the sides were kind of in on the inside, like it was caving in a little bit. So we always want to make sure, the vertices are always kind of on the outside. We never want a vertice, like a point coming in. But so far, I haven't seen Alex do that to us yet, so I'm not going to worry too much about the differences of those two. We should just be able to add the four angles together to get 360. So now I'm going to add my like terms. 105 plus 80 plus 39, is 224. So I have x come down, 224 came down, it was combined for these three, equals 360. So now I want to know what just x is, so I'm going to take this 224 and do the opposite of what's being done. I'm adding it on this side, so I'm going to subtract it from both sides. Because 224 minus 224 cancels out. Any number minus itself cancels out. So I have x drop down, and then 360 minus 224 is 136. So I know that x has to be 136. It has no choice. There are no other options there. All right. So this is just kind of looking at a parallelogram, and this shouldn't have popped up quite yet, but that's okay. So what do we notice about the parallelogram? Or about the word parallelogram. So it contains the word parallel. We have parallel right here. So if we know that it contains the word parallel, hopefully that kind of helps us lead into the idea that we are going to be dealing with some parallel lines here. If you don't remember what parallel means, it's two lines that are in the same plane and they never intersect or cross. So they're always the same distance apart. So you can kind of think of, if it's a long straight road, the two sides of the road should be going side by side. They should be the same distance apart the whole time. We're not taking into account any turn lanes or anything like that. We're just going to pretend like it's a nice straight line or straight road that, is very consistent. Or the sides of a table, as long as it's a rectangular table again, that we have two sides of the table that always are the same distance apart. All right, so finding measures involving diagonals of parallelograms. So parallelogram is a quadrilateral with two pairs of parallel sides. This is the basic definition of parallelogram. If we hear the word parallelogram, opposite sides are parallel. So I can see the top is parallel to the bottom, so I can see this little parallel marks. Whenever you see the little arrows, sometimes they're actually connected into triangles, or sometimes they're just arrows. So I have the top and the bottom, and then the left is parallel to the right as well. So, and I'm using two marks, so I have 1 to 1, 2 to 2. That's the only reason there's more than one. I try not to just use colors, because depending on if this was printed in black and white or if we were having difficulty seeing colors, some of us don't see all of the colors because we're colorblind or something like that. I want to make sure that we can still tell the difference with those things. So if I were to print this PowerPoint, you probably wouldn't very, very easily be able to tell the difference between this dark pink and the blue. The blue might be a little bit darker, but it kind of depends on the printer. So matching up the numbers is just to kind of back up there. So 1 to 1, 2 to 2. Okay, so the top and the bottom and the right and the left are parallel. All right, so what have we learned about parallel lines and transversals? Well, we've learned a whole bunch about parallel lines and transversals when we were doing that. So if I have two parallel lines, say the top and the bottom, this right side here is considered a transversal. It's crossing the top and the bottom. That's what transversal means. So with those ones, we can do alternate interior angles are congruent, alternate exterior angles are congruent, corresponding angles are congruent, or consecutive interior. So these two, right, one right after the other, are supplementary, which means they add up to 180 degrees. So that's actually one of the properties we're going to look at here. And I can do the same thing across the bottom or the top, either way. It's going to be, they match. Because I have the left and the right parallel, this bottom would become a transversal. So I have two consecutive angles. I have the two bottom angles here. And they would also have to add up to 180 degrees. So if we go to the next page here, this is something that I just like to throw in here because when I hear students say parallelogram, for whatever reason, this is always what I hear and I love it. All right, so that's just my silly little funny Baymax fist bump because I always hear whenever I hear parallelogram for the first time when students are saying it, I hear parallelogram. So it's just my fun stuff. Ooh, wasn't supposed to click on that again. All right, so all parallelograms share 5 additional properties. So we already know definition is that opposite sides are parallel. So now let's look at 5 additional properties that come with parallelogram. So the first one is that opposite sides are also congruent. So opposite sides are parallel, opposite sides are also congruent, meaning that they're the same. So if I know the top measurement, I know the bottom. If I know the bottom, I know the top. If I know the left side, then I know what the right side is. So for example, if the top is 5 centimeters, the bottom is also 5 centimeters. Or if the left side is 2 feet, then the right side is also 2 feet. So sometimes they're only going to give me 1 or 2 measurements, but I can definitely fill that in because if I know one side, I know the opposite side. All right. The next property is going to be opposite angles are congruent. So this means going from one vertex all the way to the other side like this. It doesn't mean going like from top to bottom like this. It literally means going across the entire thing like a diagonal. Okay. So for example, if the angle marked here is 95 degrees, then the other angle that I have marked here, which is opposite, is also 95 degrees. So we can definitely figure that out. So they might give us 1 and they want us to go to the other side here. Okay, so opposite angles. So for the most part, it's not just the most part, if we're looking at a parallelogram, opposites are parallel, opposites are congruent. It's a pretty easy way to remember that. You wouldn't have parallel angles, so we wouldn't say that, but their opposite angles are congruent. All right. So the next one we have here is, where is it? There it is. Consecutive interior angles are supplementary. So I've already kind of talked about that when I was talking about parallel lines and transversals. So using the 95 from the previous example, either consecutive angle would be, so if I know consecutive angles, again, that means one right after the other. So if I look at this 95 and I'm going to cross over to this one, this is one angle right after the other. Or I could go this angle and go to the one down here. That's one angle right after the other. So if I know they add up to 180 degrees, I'm just going to subtract what I have to fill that in. So that would be 85 degrees. Either one would be 85 degrees. And if I know one, the opposite angle has to be the same. So this is just kind of a pattern going around here. So it would have to be 85 degrees in this example. Okay. And this again has to do with parallel lines and transversals. So we have alternate interior angles formed by diagonals are congruent. So you can see I kind of cleared off the parallelogram for a moment so that we can kind of see a little better because it was getting a little full there. So I want to connect the diagonals. So there's one diagonal. I could have also done it the other way. So if we look at this, this again has to do with our parallel lines and transversals. Now my transversal is the diagonal, right? So it's actually crossing the top and the bottom at the corners. It's also crossing the left and the right side, again, at the corners. So I can use both parallel lines here. So if I use the top and the bottom, I go from parallel line to transversal, and we call these alternate interior angles. They're on alternate sides or different sides of the transversal, and they're inside the parallel lines. So they're in between, right? They're inside this parallelogram. And I can do the same thing on the left and the right side. So I can go from parallel line to transversal, parallel line to transversal. So alternate interior angles formed by the diagonals are congruent. This is only useful in a diagram if they already connect it. So you're not going to be drawing a diagonal by yourself and creating this, but they will put this in some of our diagrams for us where we have to do this. We can also go the opposite direction. I don't know if I actually do that. No. So I could have also connected this one and had the exact same situation with the alternate interior angles. But this next one we're going to look at is the diagonals bisect each other. Bisect means to split in half. Literally, it's going right through the midpoint. So if I connect these two, this point where they cross is the midpoint. And since they bisect each other, it means that this section on the left top is congruent to this section on the bottom right. And if I go on this diagonal, then I have this section on the bottom left is congruent to this section on the top right. So it literally is the midpoint. It cuts those two lines in half. The two lines are not congruent. Be careful about that. That's going to be one of our special properties for a different parallelogram. But a basic parallelogram does not have the two diagonals being the same. Or congruent. Just that it cuts them in half. All right, so now we can see here are the 5 properties, and this is the way you have it on your notes page. I just kind of broke it down a little bit bigger and brighter when I was doing the other one there. So these are the notes that you have on your notes page. And what they're going to give us is different scenarios based on these ones. And we have to use one of these properties to solve a missing piece. So in this case, I can see X is missing, but that's not all they're asking me for. So let's go ahead and read the problem. So consider parallelogram EFGH below. So as soon as I hear it's a parallelogram, all of these properties apply, plus the definition of opposite sides being parallel, because they don't actually have that listed in the properties here. That's the definition. So the information given in the figure, we're going to use the information given in the figure to find the measure of angle EHF. So we want this little guy here, X, and angle E up here on the top. So let's go through and we're going to start doing this. So if I look at this side here, we're going to look at opposite sides are congruent because I know that this side is 6 and this side is 6x. Well, they have to equal each other. They have to be the same. So in order for 6x to equal 6, I'm going to divide the 6 away, and that means that x has to equal 1 because they have to both be 6. I have no choice there. So there we go. I have my x. So now I'm going to look at opposite angles being congruent. So I'm kind of going through and picking and choosing which ones are the easiest ones. They're not necessarily any easier or harder than any of the others, but for whatever reason I did opposite sides first. Now I'm doing opposite angles. So I'm looking at this one. If I'm looking for E and I already know what G is, well, then E has to equal the same thing. I know that angle E has to be 97 degrees because opposite angles are congruent. All right, last one. We're going to look at EHF. So that's this one down here that I've marked in pink. And I've circled property 4 here. Alternate interior angles formed by the diagonals are congruent. So they've connected a diagonal for us, right? And I have this top one up here is 44 degrees. So if I go to the alternate side, but still stay in between the parallel lines here, so I don't leave, this is the alternate interior angle. So that means that angle EHF has to equal 44 degrees. So there's not a whole lot of crazy mathematics happening here. It's more just matching up the properties. Do we know which property to use and how to apply it? All right. So now we're going to look at a little proof here. Completing proofs of the theorem involving sides of a parallelogram. So use the given information to complete the proof of the following theorem. If opposite sides of a quadrilateral are congruent, then it is a parallelogram. So you notice we're not starting with parallelogram. We're starting with a quadrilateral that has opposite sides congruent. We're proving this. And if that's true, then it must be a parallelogram. So we're kind of going backwards. We're not starting with a parallelogram. We're proving it. So whenever we want to prove parallelograms. So to prove a parallelogram, we have to prove that opposite sides are parallel in order to prove that this is a parallelogram. That's the best, usually easiest way to do that. It's not the only way, but a lot of the time we go back to the definition. So by definition, a parallelogram is a quadrilateral in which both pairs of opposite sides are parallel. Use this definition in your proof. So they're directing us in that way too. Alex actually pushes you that direction. So the very first thing you do with the proof, you look at what you are given. Look at your diagram. What's your given information? What am I trying to prove? Because this is where I'm starting. This is where I'm going. You need to make a plan. How do I get from where I'm starting to where I'm going? You need to kind of think through it. It's not necessarily the easiest as far as just go, go, go. You need to make sure you've got a plan. So take a second and look at it. So the first thing I always do is I go through and I mark up what we're doing. So my plan is first we're going to prove that these two triangles that it's created are congruent. And then we're going to use Cpctc. I can even see that down here. And this fill in the blank gives me a little bit more clues as to what I'm doing. And this means corresponding parts of congruent triangles are congruent. So once I prove the two triangles are congruent, I can actually grab different parts that are corresponding to each other that are congruent. Say the left and the right side and the top and the bottom, which is partially where I'm going to be going here with the different pieces. All right, so we're going to mark up our diagram. So here's my given information. I was given that QR is congruent to ST, QT is congruent to RS. So I have that marked in my diagram here. And they already put the given in there for us. That's the very first thing you should put in your proof, because that's what you're starting with. You can't go anywhere until you have something to start with. All right, so now if I'm thinking about how to prove two triangles congruent, if we go back to that section a couple weeks ago, I can use side, angle, side, angle, side, angle, 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 side, or side, side, side. So I have to be able to prove one of those four things. Because I have two sides congruent to each other already, I'm either going to do side, angle, side, which would mean I'd have to be able to prove something about Q and S, or side, side, side. Those are the only two that use two sides or more. So I can't prove anything about Q and S. Not yet, anyway. But I can prove something about this third side because it's a shared side. They share RT, right? So I even have it down here. So we can use one of these two. And since nothing can be proved about the angles, we're going to look at that third side. And what do we notice about the third side? It's shared by both triangles. If I were to split these two triangles apart, they still would both have that side RT, right? So RT is going to be equal to itself. Anytime I say something's equal to itself, well, yeah, that's kind of obvious. So I kind of relate that like, okay, it's a reflex. Of course that's equal to itself. You know, so it's a little easier for me to remember that property if I kind of make that connection. Like that it's just, of course, it's a reflex. All right, so now I have side, side, side for both triangles. All three sides of this left triangle are congruent to the corresponding sides of the right triangle. So that means I can say the two triangles are congruent to each other. RQT is congruent to TSR. Be careful about this order. This can get you marked wrong. You need to make sure it's in what we call corresponding order. So R corresponds to angle T, Q corresponds to angle S, and T for this left side corresponds to angle R for the right side. So you need to make sure that you're going in the corresponding direction, not the same direction. But it would be R, Q, T. So then I'd start at T and go to S and then R. And this is side, side, side congruence, because I proved all three sides of one triangle are congruent to all three sides of the second triangle. So now I have congruent triangles. I can use Cpctc. So I'm going to use angle 1 is congruent to angle 4. Those are corresponding to each other. R on this side is congruent to T on this side. Okay, so 1 is congruent to 4, and 2 is congruent to 3. So we're not using the alternate interior angles yet, but we are going to use those to prove the parallelogram, okay? So we're actually grabbing those because they're corresponding parts. I know they're congruent, but hopefully we're also noticing that those are alternate interior angles, because that's what we're going to go to next here. So now I have these alternate interior angles. So if I have 1 is congruent to 4, well, 1 goes from this red transversal to the left side, and this goes from the red transversal to the right side. If I have alternate interior angles congruent, then the lines are parallel. So I can actually do that with both. QR is parallel to ST, and then I can do the same thing with the top and the bottom because of 2 and 3. It goes from transversal to the top, transversal to the bottom. So if alternate interior angles are congruent, then the lines are parallel. So this is going backwards. Again, I didn't know the lines were parallel. I'm proving they're parallel. So now that I know that the left and the right are parallel and the top and the bottom are parallel, well, that's my basic definition of a parallelogram. So I can say that it is a parallelogram, and I can use the reason of it. That's the definition. All right. I think we have one more proof. Oh, no. Okay, we're going to do a coordinate grid type proof. So finding the coordinates of a point to make a parallelogram. Students always tend to make this one a little bit bigger than it needs to be because it's coordinate grid, I think, or coordinate proof type idea. So we're given 3 vertices of a parallelogram, and we're being told to find the 4th one. So we want it to look like a parallelogram. So if I can kind of connect that in my head, since this one's kind of slanted a little bit, I want this one to be slanted at the same angle, and then I would connect it so that it actually looks like a parallelogram, kind of like that, pushed over rectangle, basically. So first, we're going to label the vertices A, B, and C like this because A, B, C, D just makes it a little easier to reference. If I say, vertex A, vertex B, vertex C, D, instead of having to reference the points constantly. So if we label them like this, it makes it a little easier. And then I'm going to go from B, so this one here, to C, this one here. I want to know how far down am I going and how far to the left am I going. I'm going to do that exact same movement on A. So all I'm doing is I'm going to match the slope, because remember, these have to be parallel lines, so the slopes have to match. So however I get from B to C, I need to do the same thing to get from A to D. So to find how far down, we subtract the y coordinates. So y is 4 and -1, so I went -4 minus 4. So we're going down 5, it's -5, so that means down. So we went from B to C, I went down 5. So right here we can see we're going down 5. To find how far to the left, we're going to subtract x coordinates. So I have 3 and 6, so I have 3 minus 6, which is -3. Negative means left. So we're going to go left 3. So I'm going to do this exact same thing on A. So since opposite sides of a parallelogram are parallel, AD must have the same slope as BC. So we find the coordinate of D by moving the same way from A. So I'm going to go down 5 and left 3. So we land on -4, or we started on -4, 1. That's A. And I'm going to go down 5. So I'm subtracting from the y, and I'm going to go left 3. So this is another way you can do this with a coordinate. You can actually just subtract right from the coordinate. So if I have -4 minus 3, I land on -7. And if I go from 1 minus 5, I land on -4. So I went down 5 and left 3. So this would be my new coordinate. So this one, again, it's always a little different because students, for whatever reason, make this one a little bit more difficult, I think, than it needs to be. They see this and they think that it's a much bigger problem than it is. It's just matching those parallel lines. So I want to do the same thing. If I go down and left, I want to go down and left the exact same, and that will be my point. All right. So now we're going to go to section 2, and we're going to look at those same 5, or similar to the same 5. There's actually one slightly different on here. But we're going to look at testing for a parallelogram. So now what we're doing is we're going to start with a quadrilateral, a 4-sided figure. We're going to decide, is it a parallelogram? So we're actually going to kind of go backwards from what we just did. So we still have these properties though. So show that both pairs of opposite sides are parallel. So if we can show the definition, if both opposite sides are parallel, well, that's definitely a parallelogram. Or if we can show that both pairs of opposite sides are congruent. Both sides of opposite angles are congruent. So these three are pretty much the same as what we did before. But now we're starting with a quadrilateral, and we might see opposite angles are congruent. Okay, I know it's a parallelogram. Or I see that opposite sides are congruent, sorry. Oh, yep, that's a parallelogram. Or if they are parallel, yep, that's a parallelogram. This fourth one is a little different. So this is show that one pair of opposite sides are congruent and parallel. So it's one pair. So in this case, it's the top and the bottom. I can see the congruent mark, and I can see the little parallel triangle. So this works. It wouldn't work if they were split, if you had like the top and the bottom pair are congruent and then the parallel marks over here. That doesn't work on this property. It needs to be one pair of sides. So either the top and the bottom or the right and the left. And then you can use this piece. Because we can go further than this to show that alternate interior angles are congruent. And then we can show that the diagonal is congruent. So we can actually go through, if we went through a whole proof on this one, and we could use side angle side to show that the two triangles were congruent if we drew a diagonal here. And then once the two triangles are congruent, we can keep going and continue to show that opposite sides are parallel, kind of just like we did on that last proof. Or two problems ago on the proof. So this one's just kind of a continuation a little bit of that idea of proving triangles congruent when we do a diagonal. Or the last thing we can do is show that the diagonals bisect each other. So if I see this idea where the diagonals are bisecting each other, that means it's a parallelogram immediately. Okay, so this is parallelogram diagonals, converse. Converse means backwards, basically. It's not, before we said if we have a parallelogram, diagonals bisect each other. Now we're saying if we have a quadrilateral where diagonals bisect each other, it is a parallelogram. So it's kind of, we're flipping the statement over. Okay. So now let's look at the problem here. So given the information marked on the figures below, classify each quadrilateral as a parallelogram or not necessarily a parallelogram. It might look like one. We have to be able to prove it. So don't just jump ahead and go, oh, yep, that looks like one. You need to be able to prove it. Okay. So it might not necessarily be one. Doesn't mean it's not. It just means I can't necessarily prove it with what I'm given. So note that each figure is drawn like a parallelogram, but you should not rely on how the figure is drawn in determining your answers. So that's a big one. Do not trust the diagram. They're all drawn to look like parallelograms. If necessary, you may learn what the markings are on the figures. So I'm going to go through these markings as well, but if you forget and you're on Alex, you can always click on this and it'll teach you again what all the little markings mean on the diagrams. We do really need to learn that because that's how Alex is going to present it to us every time. And it's not just Alex, it's every math book, every math class, we present it like this. All right, so we have this first one here. So I have parallel, right? So the top and the bottom are parallel. And then I also have this angle here and this angle at the bottom here that are congruent to each other. So if this is a transversal, this diagonal going through the middle, then I would have from transversal to the side, the left side, transversal to the right side. Well, these are alternate interior angles. So if alternate interior angles are congruent, then the lines are parallel. So that means that AC and BD are also parallel. Well, if the top and the bottom are parallel and the left and the right side are parallel, then guess what? It is a parallelogram. That is our definition. Okay, so I'm showing you I'm using alternate interior angles here to show that the two sides are parallel to each other. So the left and the right are parallel. So that means that I have opposite sides parallel. That is our definition. So yes, that's a parallelogram. All right, the next one, we're looking over here. So we have consecutive congruent sides does not prove parallel lines. So I have this side is parallel to this side. So the top is parallel to the right. And then I have the bottom is parallel to the, sorry, not parallel. Why am I saying parallel? The top is congruent to the right. The bottom is congruent to the left. So this doesn't necessarily prove a parallelogram. This actually is what we call a kite. but we don't go too far into that on this section. So this is just a different quadrilateral. It's a different type. It is four-sided, but it's not necessarily a parallelogram. So we're just going to click on that guide here. Not necessarily. Doesn't mean no 100%, but it's not one of the properties we're looking for. Okay, so now we have a parallel side and a parallel side, and we have a congruent side and a congruent side. Remember, we do have one of our properties up here that uses parallel and congruent, but they have to be the same side. This doesn't necessarily help us as far as going to the next piece. Because now if I were to connect the diagonal, kind of like this one's connected up here, I would be able to show alternate interior angles congruent, but only for the parallel lines. So that's not really going to help me, but I could show those angles are congruent, and then the diagonal will match itself. So with this one, it's the side and the lines need to be the same, because I can't go far enough to apply one of our four properties for side, angle, side, angle, side, angle, 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 side, or side, side, side. I'd be missing one of the pieces there. So it won't work. We can't do angle, side, side, and you can figure out what that spells on your own. You're not allowed to use that one. That's not a proper theorem for this one. So it doesn't actually work. There are ways to disprove that one. So we can't necessarily prove this. All right, last one here. So we have consecutive angles here on the inside are congruent. So I have, it's not alternate angles, so we're not crossing the transversal. It's the same angles in the triangle. And this would prove, I could use Isosceles Triangle theorem to prove that the left is going to be congruent to the right, or the top, because I can go opposite angles are, the sides opposite the congruent angles in a triangle are congruent. That's the Isosceles Triangle theorem, the converse of it. So I could do the same thing on this one, but that actually brings us to a similar situation as this top one here. But and I've got it marked alternate interior angles, don't I? I marked that one wrong. Ooh. So definitely don't mark it the way that I marked it on here, because I accidentally looked at that funny when I did it on the PowerPoint here. These are not alternate interior angles. So I should have marked not necessarily. This does not work in that same way. So we can't use this. So make sure, hopefully we're listening and we're not just watching this, because this is not correct. All right, so let's go ahead and take a look at this one. So we're going to consider quadrilateral JKLM below. So they give us our little coordinate grid. They give us the points as well. And we're going to find, we're going to complete the following. So we have A, B, and there's a C part as well to determine if JKL is a parallelogram. So first what they're going to have us do is find the lengths of two sides. So we're going to find the length of JK, which is this top right side, and LM, which is the bottom left side there. I know it's kind of tilted, so that's why I'm saying both, bottom left and top right. So we're going to go through and we're going to use the distance formula. So here it is, if we need to see it again. When we have 2 points, we have x1, y1, x2, y2. This means 0.1, 0.2. And we're going to plug it in here, okay? So I'm going to label this so you can see, and I have these already marked out here so that I can see this, and this should be on your notes page as well. It's going to be a little taller on your notes page, but it's definitely there. So here I have it marked, x1, y1, x2, y2. So I love labels. Makes it so much easier when you're going through and getting things done. Now all I have to do is fill this in. So if I'm looking for x2, there's my x2. If I'm looking for x1, there's my x1. So I'm just filling this in, x2, x1. And then y2 will be my next piece. So that's 2, and then y1. Don't take away this minus sign in the middle here, even though it's minus 1. This minus is part of the formula. So we want to leave minus -1 because that actually is going to turn into a plus sign when we get there. So 3 minus 8 is -5. And then you notice how I put a big purple plus sign there because minus negative turns into plus. So we have 2 plus 1 is 3. Now we're going to square them. So negative 5 squared, that's negative 5 times negative 5 is 25. And then 3 squared, remember that's 3 times 3 is 9. And I'm going to add them together. 25 plus 9, I get 34. I'm not going to reduce that anymore because number one, 34 doesn't break down into any squares. You'd only reduce that if you could take a square root out of it. Otherwise, just leave it square root of 34. They do not want any decimal approximations. Okay, they may have you reduce it if you could take out a square, like 4, 9, 16. Like if you could divide it by one of those numbers and then take the square root out, then they'd have you do that. But so far, I've seen them almost always end up something like this. Or it's a number we can't take a square root out of. And if we tried to break this one down, it would just be 2 and 17. Well, neither one of those are a square. All right, so let's do LM here. So I'm going to reset this. So now I have 0.1 and 0.2. Okay, so I scooted my labels over here. So if you're labeling it on your own paper, that's definitely a good idea. I 100% suggest you label it. Just make sure you're paying attention. Now we have a new 0.1 and a new 0.2. All right, so x2 minus x1 and y2 minus y1. So here we have our pieces, and this is minus negative again. You can see I'm putting my purple plus sign in. So I have 4 plus 1 is 5, and then I have another purple plus sign here because it was minus negative 3. So negative 6 plus 3 is negative 3. So now I have 5 squared, so 5 times 5 is 25. Negative 3 squared, remember negative 3 times negative 3, that's 9. And if you notice, we're ending up the same. We actually wanted that. So now I add them together and I get 34. So now I'm going to put up here. So the two lengths are congruent. Yay! So and I even marked them. We have blue and we have red. So the top and the bottom here are congruent to each other. So now if you remember, there was that fourth property that we were just doing on that other page. If I can prove that they're also parallel to each other, it's a parallelogram. So that's what they're going to point us toward. So the next part here, they're going to have us look at the slope. And oops, that slope shouldn't be there yet, but we'll go through and explain how I got that. It was just an animation, oops. All right, so we're going to find the slope of JK and the slope of LM because we're going to try to prove that these are parallel lines. Because if they're both congruent and parallel, we've done our job. All right, so here's the slope formula. I put it up here kind of to review, and then it's also down here again. So here are my labels, back to what they were. So if you've already got these labeled, great. We're going to use the same labels that we just did on the last step. So now I'm going to go y2 minus y1. So I have 2 minus negative 1. And then on the bottom, I'm going to go x2 minus x1. So, and again, you can see this purple plus sign popping up because it was minus negative 1. So I have 2 plus 3. Sorry, 2 plus 1 is 3. And then 5 minus 8 is negative. I'm just messing up every time I say these. 3 minus 8 is negative 5. If you remember me from math class, I do that every once in a while where for some reason my brain is thinking one thing and I say it out loud before I'm ready to say it. So silly, fun stuff, right? We all have our little quirks there. So it's 3 divided by negative 5. So, or 3 over negative 5. So this is my rise and my run. For this line, every time I go up 3 or down 3, then I'm going to run 5. Okay. So this one, if I go 1, 2, 3, then 1, 2, 3, 4, 5. Oh, look at that. I landed right on K because I went up 3 and left 5. That's all this tells me. So now as long as I get the same slope for LM, we are golden. This is a parallelogram. So let's go ahead and check that. So I'm going to reset I'm going to go back to L and M. So I'm going to go y2 minus y1, x2 minus x1. So now again, my purple plus sign's popping up here because it's minus negative 3. So negative 6 plus 3. And also a little purple plus sign down here. So I did them both at the same time because I also have a minus negative 1 on the bottom. So we get negative 3 on the top and we get positive 5 on the bottom. Now, I know this throws some students off because this is 3 over negative 5 and this is negative 3 over 5. This negative, you can put it on the top, you can put it on the bottom, you could even put it right here in the middle. As long as there's only one negative, it actually means the same thing. So what this means, if I were to go from this one, I would drop down 3 and run 5 this way. But it's the same idea. I could also go 1, 2, 3 up and 5 left, and I would still land on that same one. So I can move that negative to top or bottom. It doesn't change the actual number. Okay, so yes, these are in fact the same slope, even though the negative's in a different place. All right, so now let's look at part C here. So we have from part A and B, we can conclude, so the quadrilateral is a parallelogram because it has one pair of opposite sides that are both congruent and parallel. So that sounds pretty promising. The second one here, I'm going to back up a little bit. The quadrilateral is a parallelogram because it has one pair of opposite sides that are parallel, even though those sides are not congruent. Well, we just proved that the top and the bottom are parallel and congruent, so we did prove that, so I'm crossing that off. I already know that's not true. The third one here, the quadrilateral is a parallelogram because it has one pair of opposite sides that are congruent. Yay, we proved that in part A. Even though those sides are not parallel. Well, we just proved that in part B. They are parallel. The quadrilateral is not a parallelogram. Well, we know it is because it's one pair of sides is both congruent and parallel. So we know it is a parallelogram, and that it cannot be determined. Well, we can determine it. So the only thing that I didn't cross anything off on is that first question. There, so that's definitely my answer. I know it's a parallelogram because one pair of opposite sides is both congruent and parallel. Okay, so let's look at rectangles. These are our special parallelograms. We're going to start to get into kind of specializing. What we've looked at for the last 2 sections were basic kind of parallelograms, just that very basic shape that it looks like a rectangle pushed over a little bit. So now we're going to look at a rectangle. So finding measures involving diagonals of a rectangle. So let's think real quick. What do we already know about rectangles, which are special parallelograms? So if I know it's a special parallelogram, I know opposite sides are congruent and parallel. So we can see that happening here. So here are my opposite sides congruent. I didn't mark parallel, but that's okay. We also know that opposite angles are congruent. Because it's a rectangle, I should also know that they are 90s. So hopefully we all recognize the fact that if it's a rectangle or a square, that we have 90-degree angles. And then the diagonals bisect each other. So we know that already. The diagonals bisect each other. That was part of a parallelogram. When we are talking about a rectangle, and sorry, those ones are a little hard to see, but there are marks here showing that they're bisecting, that the segment here is congruent to the segment on top. Special for a rectangle, the diagonals are congruent. So only if it's called a rectangle can we say the diagonals are congruent. So then now those 2 marks disappeared that you could barely see. Now they're all orange because now this midpoint is the midpoint for all 4 pieces, and all 4 pieces are the same. Only in a rectangle. Okay? And this is kind of one of those tongue twisters. A square is a rectangle, but a rectangle is not always a square. Okay, so be careful about that. Square has a lot of the same properties of a rectangle. It actually has all the same properties of a rectangle, but a rectangle does not have all the same properties as a square. So just be careful when you're naming these things and paying attention to the properties. All right, so in the rectangle below, we have AE is equal to 4x plus 5. BE is equal to 6x minus 7. And the measure of angle AED is 118 degrees. Find AC and the measure of angle ECB. All right, so first, we're going to go through and we're going to label the diagram. I always label the diagram. I push this a lot because it's so much easier to picture if you label it. If you don't have the notes pages, you should be writing this out and drawing these diagrams. It only takes a second. They do not need to be perfect. It just needs to be, rectangle-like so that you can write it out and actually picture where this information is going. So here's AE, and that's 4x plus 5. And then we have BE, and that's 6x minus 7. And I do like my color coding. If you know me from class, I really like to color everything. And then I also have this angle AED that is 118 degrees. All right, so that's my given information. So now we're going to go through and find AC and angle ECB. So in order to find AC, which is this whole length here, well, part of that is x. So we're going to need to solve for x. Even though they're not actually asking us for x, I need to know what it is. So remember, if this is a rectangle, which they told me it was, the diagonals bisect each other and they're congruent to each other, which means that this red line here is congruent to this blue line here. Congruent means that they're equal to each other. So we already know part of AC. I know half of it. Half of it is 4x plus 5. So if I can figure out what this 4x plus 5 equals, all I have to do is double it, and I'll have the entire diagonal, right? So we're just going to go through and use the two diagonals to do this. So this was already being said out loud, but here it is. So we have 4x plus 5 equals 6x minus 7. I know that these two pieces are equal to each other. Diagonals bisect each other, meaning that this is the midpoint, and in a rectangle, they are congruent. Can't say it enough times. The more times we repeat this and we listen to it, hopefully the more time these properties sink in. All right, so we're going to start to group like terms. So I'm bringing my 4x over here to the right side. So 4x minus 4x cancels, 5 drops down, and I have 6 minus 4, which is 2x, and the negative 7 drops down. So now I'm going to bring this 7 over to the left side. I'm just trying to get x by itself. First, I want to group some like terms here, but my ultimate goal is to figure out what is x. So 5 plus 7, we get 12. 2x drops down, and the 7's cancel. So now my last step here is to divide by 2, because it's being multiplied by 2. So if I divide by 2, 12 divided by 2 is 6, and that means that the 2's cancel, and I have x. So again, this isn't actually one of the answers that I want. They didn't ask me what x is, but I needed to know what x was so that I can go back and plug it in, so that I can figure out what AE equals. So now I'm going to go over here, and you can see here's AE at the bottom. So I have 4x plus 5. Well, I know x equals 6. We just figured that out. So 4 times 6 is 24, plus 5 more is 29. That's half of what I'm looking for. Remember, that's just AE. I want the whole thing. I want AC, which is twice as long, so I'm going to multiply by 2. So 29 times 2 is 58. So this one definitely requires a few more steps. It requires us to understand a little bit more about the diagonals and then apply the algebra to it. So AC is 58. Look at the angle they want us to find. So they want us to find angle ECB. So I've got that marked down here in green. So the way that we're going to do this is we're going to kind of divide it up. We're going to bring the one angle that we do have over into this kind of triangle here. And then we're going to think about what we know about triangles. So first, let's bring this 118 over. And how can I just bring this over? And this is actually for this section here. I just forgot the arc. Well, anytime we have two lines crossing, we have what are called vertical angles. So anytime I have two lines crossing, I can go across the vertex, and those two angles will be congruent to each other. So I know that this big angle here is also 118 degrees. I also know that the angles of a triangle have to add up to 180 degrees. So that means that angle B plus angle C plus the 118 that's in the middle here is equal to 180 degrees. So I know this. This is our triangle angle sum theorem. And we use this one, quite a bit. So hopefully we recognize that idea, that the angles of a triangle add up to 180 degrees. The other thing I know, which is a little bit, it's kind of going back and remembering when we were doing isosceles triangle, and just kind of applying that here, because the diagonals are congruent, so we already know that, we did that in the first part here, and they bisect each other, that means that we have created, all the triangles that are created here are isosceles triangles, meaning that they have at least two sides congruent to each other. So I know that this blue one I have marked up here, and then this bottom right one here, EC, would be congruent to each other. Because again, this is the midpoint of all the diagonal pieces. So those two are congruent. And since it's an isosceles triangle, what I also know is that the base angles, or the angles opposite those congruent sides, will be congruent to each other. So that means that angle C and angle B are going to be the same measurement. They're going to be congruent to each other. So in my little formula here, I'm going to replace B with C. I'm going to substitute. Because I can't solve if I have two variables. But if I know that they're the same, I can just say instead of angle B, I'm just going to solve for angle C. I'm going to substitute it in. So now I can add my like terms. I have angle C plus angle C, and I can add those two together because they're the same angle. So I have 2 angle C plus 118 degrees equals 180. I'm going to subtract the 118 from both sides, so I'm getting 2C by itself. And then I have 2C equals 62 degrees because I subtracted here, and the 118s on this side cancel. Anything minus itself cancels out. And then my last step is, I don't want to know what 2 of angle C is, I just want to know what 1 is, so I'm going to divide by 2. So 2 divided by 2 cancels, and 62 divided by 2 is 31 degrees. So that tells me that angle C, which is the ECB down here, I was just being a little simpler for our formula here, is the 31 degrees. And if they would have asked me what the angle on top was, it would also be 31 degrees. They both have to be the same because I've created isosceles triangles. And it wouldn't have mattered which triangle they asked me to look at inside of this piece. As long as it has the 2 diagonals on it, then it'll work this way. Now, if they asked me to look at one of the larger pieces, one of the larger triangles, ignoring one of the diagonals, then it would not be an isosceles triangle. But because they're asking me to focus on one of the 4 triangles that are created, it is isosceles. All right, so we're going to go to the next piece here. So now we're going to look at the conditions for quadrilateral. So we have a bit of notes to fill out here. And I know it's very wordy, so we're going to go through this one. And some of it is just kind of review on what a quadrilateral is. So a quadrilateral is a 4-sided figure. We've already talked about that. Quad means 4. A parallelogram is a quadrilateral with 2 pairs of parallel sides. We already know that. That is the definition of parallelogram. The following 4 conditions guarantee that a quadrilateral is a parallelogram. So if a quadrilateral in which both pairs of opposite sides are congruent, if a quadrilateral in which both pairs of opposite angles are congruent, it is a quadrilateral in which the diagonals bisect each other, or it is a quadrilateral with at least 2 pairs of opposite sides that are both parallel and congruent. This should say 1 pair, actually. Sorry, that was a typo. All right, so that's just review, kind of very quick review of what we just went over on the last section. And then this part says, a rectangle is most commonly defined as a quadrilateral with 4 angles, 4 right angles. The following 4 conditions guarantee that a quadrilateral is a rectangle. So it's a parallelogram with 1 known right angle. That's all I need. If 1 angle is right, I can actually find out that all the rest are right, because opposite angles would have to be congruent, consecutive angles have to add up to 180. So if I have 1 right angle and I know it's parallelogram, they will all end up being right. It is a parallelogram with congruent diagonals, so that's special to a rectangle. It is a quadrilateral with 4 congruent angles. So if all 4 are congruent, 360 divided by 4 is 90. And remember, if it's quadrilateral, they have to add up to 360. It is a quadrilateral with at least 1 right angle and all other angles congruent to each other. So if I don't know it's a parallelogram, I'm just told it's quadrilateral, but I have at least 1 right angle, and then I know the other 3 are congruent to each other, it will also work out where I can solve that to come back to find that they are all 90-degree angles. And finally, it is a fact that a rectangle is also a parallelogram, and any parallelogram is also a quadrilateral, so we can kind of work our way backwards there. A rectangle is a special parallelogram. Parallelogram is actually a special quadrilateral, okay? So they kind of, there's this chart that I hope I do have on here that kind of shows you the progression of these ones. So hopefully we'll look at that here in the next couple slides. So the given information marked on each figure below, select all classifications that must be true. So this means that there can be more than 1 classification. It means we can check more than 1 box if we are able to. So note that each figure is drawn like a rectangle, but you should not rely on the way the figure is drawn in determining your answer. So rely on what you know. What are you given as far as the marks, and what properties can you use? And again, if you need to be reminded of what the marks are on Alex, you can always click on that. It's a blue link that will show you what all these markings mean. So on this one, we have all four-sided figures. So all of them are 4-sided figures. Every single one of these are 4-sided. So immediately, I know that they are all quadrilaterals, right? Every single one of these is a quadrilateral. because they're four-sided. That's all that's required to call it a quadrilateral. So the second piece that I have is that in this one, I have opposite sides are parallel. I have the top and the bottom, I have the right and the left. Okay, well, I know that that's a parallelogram. I also know, sorry, it's stacked a little bit here, diagonals are congruent on this one. I can see that this is a midpoint, and this piece is congruent to this piece, is congruent to this piece, is congruent to this piece. So this guy is most definitely a rectangle. So it's all three. It's a quadrilateral, it's four-sided, it's a parallelogram because opposite sides are parallel, and it's also a rectangle because the diagonals bisect and are congruent. So the diagonals bisecting would actually be enough to call it a parallelogram as well. I wouldn't have even needed the parallel marks to say that it's a parallelogram. All right, so this next one, we can't really prove anything more about this one. And sorry, this other piece, all four sides was supposed to disappear, but it's kind of right on top. So I'll fix that for later. But I do know that the top two diagonals are congruent and the bottom two diagonals are congruent. But that doesn't really help me. I can't prove anything more to go farther than it's just a quadrilateral right now. Because the diagonals don't necessarily bisect. This one could be shorter, this one could be longer, because it's not telling me that they're equal. So I don't know that it's bisecting in the middle. And I don't know anything about the sides being parallel or congruent. I don't know about anything about the angles being congruent. So we can't really go any farther on this one. It's just quadrilateral for now. We know this one, again, is a quadrilateral. But now I do see that the angles bisect. I can see that this top half is congruent to this bottom half. And this top half is congruent to this bottom half. So they do bisect each other, which means it is a parallelogram. But I don't know anything more about whether or not the diagonals are congruent. They could be, but I'm not shown that they're congruent. They look like it, right? They told us that it's drawn to look like a rectangle. But I can't prove it with the markings I'm given. So we're not going to check a rectangle there because I can't prove using the diagonals in this one. I would have to see this idea where all the pieces were congruent to each other. It was 1, 1, 1, 1. But instead I see 1 to 1, 2 to 2. So I don't know that they're the same length. They could be, but they could also be slightly different. All right. Is that the end? I think that might be the end. Let's see. That is the end. All right. So we'll go back on here. So we're on the end there. All right, so that was the end of section 3. So we may start looking at that diagram that I was talking about where it's going to show us the kind of transition from quadrilateral to parallelogram to square to rectangle to rhombus to square. There's all these kind of transitions we go through as we're getting more specialized with our quadrilaterals. So we'll definitely start looking at that next week in class. I hope that this video helped you. Again, make sure if you did not have your notes pages, that's definitely something that I want you to have because it will make this video much easier to follow. If you have any questions, please reach out to me or your independent study teacher, and I will see you next week.